So now David Torres is going to tell us about transverse integral affine foliations in Poisson geometry. Thank you.
Okay. Thank you very much, Gal, for the presentation. And thanks a lot to the scientific committee of the Congress. I'm very much honored to take part of this meeting, especially because it's post 18th birthday celebration. So I guess I got to meet Paul in person later than most of you in the audience. So that was in 2014 when I was hired by Pookie. And well, I've been there for almost 8 years. I left a few months ago to take a job in a different country. And I'm already missing things about the department, especially just bumping into Paul now and then, because I mean, those short meetings were actually quite reassuring to me. And after some time in the department, you realize that it's absolutely impossible to imagine that department without Paul, and actually the whole university without Paul. So Paul, happy birthday. I regret I cannot be there in person. And thank you very much for being such a great colleague and such a great colleague during these years. Now I'm gonna move to the talk. So as Gael presented, I'm going to talk about transverse integral affine foliations in Poisson geometry. So this is joint work with Kreinik and Fernandez, and part of it is already published and part of it is work in progress. So the goal of the talk is to discuss what's the role of transverse integral affine foliations to promote, even actually to be able to state some important results from symplectic geometry to Poisson geometry. So if you want, the talk is about foliation theory and Poisson geometry being useful to each other. Now, the main result and the motivating result that I like to promote from symplectic to Poisson geometry is a theorem of Doistermark and Heckman about the variation of symplectic reduced spaces, or the cohomology classes of symplectic reduced spaces. And what I will do, even though I imagine that almost everyone there knows very well about the result, I'm gonna spell out in detail this result. So one starts with a symplectic manifold, M with a symplectic form. So you can think of a surface with an area form, though for our purposes, surfaces they have very low dimension. You can think of a Keller manifold, for instance, or you can think of a cotangent bundle if you want a generalized trace space. And then on that symplectic manifold, we're going to have a torus acting. And the action is going to be Hamiltonian. And that means the following thing is not only the action of the torus, the compact torus has to preserve the symplectic structure. So infinitesimally, that would mean that if you take a vector V of the Lie algebra, then the corresponding fundamental vector field of the action has to basically kill the symplectic form. But on top of that, you want these infinitesimal symmetries to come from functions, first of all. So that means that specifically, if you contract the vector field with the symplectic form, that will produce a one form, and you want the one form to be exact. So you will make a choice of function for that symmetry. And secondly, you want that choice of functions to be coherent with a couple of brackets that you have in this setting. Now, the first bracket, that one is in the functions of the symplectic manifold. So with a function, one can take the exterior differential, produce the corresponding one form, and then contract it with the symplectic form and get an infinitesimal symmetry of the symplectic structure. And then, well, one defines the Poisson bracket of F and G as the contraction of the symplectic form with both infinitesimal symmetries. So that's the first bracket that we have on functions on the symplectic manifold. There's a second very obvious one in the Lie algebra, which is the given bracket. So the compatibility condition is that the bracket of the functions HU and HB has to match with the bracket in the Lie algebra, which in this case is 0 because our torus is abelian. And you can also actually rephrase this result in a more Poisson theoretic language, because actually these two brackets that you see here, they are of the same type. So you can think of a vector in the Lie algebra as a covector in the dual of the Lie algebra. So you have a bracketing covectors, and that bracket can be promoted to functions in the dual of the Lie algebra. So that's also a second Poisson bracket. And you can restate the Hamiltonian condition by simply saying that this so-called momentum map, that sends a point of the manifold to the covector h of x, that's a Poisson map that's compatible with the bracket. All right, so that's the Hamiltonian condition. And then we're going to add some topological conditions for the action. So we're going to require that the action be free and proper. And if you want to have a simple example in mind, you can think of complex space minus the origin. So the symplectic form is, let's say, the standard one, or you can think that it's the cotangent bundle of Rn minus the origin. And then you can use the diagonal action of S1 in complex coordinates. So that action is going to be Hamiltonian. And if you make a few computations, you're going to see that the momentum map, this mu, sends a complex vector to minus pi times its norm squared. Now, the momentum map in principle takes values in the dual of the Lie algebra. And here we're making an identification of the dual with the real numbers. And that identification actually is unique up to sign. And to make that choice, you use a second structure that you have in the Lie algebra or in the dual of the Lie algebra, which is simply the lattice given by the kernel of the exponential map. So if you make the correct identification of the dual of the Lie algebra with the dual of that lattice, then you will get the real numbers with the integer numbers inside. And with that identification, you have that momentum map. All right, so what's the use of these two topological conditions, the freeness and the properness? So first of all, you can use the freeness to perform Hamiltonian reduction on any value of the momentum map. You take psi in the image, and some general theory in symplectic geometry is going to tell you that that psi is always a regular value of the momentum map. So it's pre-imaged, it's a some manifold, and then you can take the quotient. Now, it turns out also that on that some manifold, the symplectic form is going to be basic with respect to the action of the torus, so you can produce a symplectic form in the quotient space, in the symplectic reduced space. Okay, so that's one way of producing a reduced symplectic manifold. And then you can use the properness assumption to basically put all the symplectic reduced spaces together and be able to compare the corresponding reduced symplectic forms at the cohomological level. So more explicitly, the properness assumption is going to tell you that M quotient T with induced map coming from the momentum map is going to be a fiber bundle with compact fiber, actually with connected fiber. And from there, what you can do is basically produce an associated vector bundle where you're replacing each fiber by its second cohomology group. Now, as we know, for nearby fibers, the identification is unique up to isotopy, and that means that this vector bundle is a flat vector bundle, comes with a canonical flat connection. And that means that if you make the assumption that the image is simply connected, for example, assuming that M is simply connected, or if you work locally around the point of the image, your vector bundle is actually a product vector bundle. So the section that at each point in the image assigns the cohomology class of the reduced space is actually a function. So this is the variation function that, as I told you, goes from the image of the momentum map to the second cohomology group of the reduced space. Okay, so you can compute this variation map in some basic examples. So I'm going to use the previous example, the one of Cn, but with n equals to 2. Now, if you see what this quotient is, well, each level of this map mu bar is going to be a free sphere. And then the action of S1 is going to give you the Hopf vibration. So you're going to have in the quotient basically spheres. Now, you can actually see this much more clearly by using the classical Hopf map that's going to send you this quotient of C2 minus the origin to R3 minus the origin. And if you keep track of what happens with this map mu bar, this map is basically going to send a point in R3 to its norm times minus pi. Now, the pre-images of points in that negative real line, they are spheres, and those spheres are going to have the corresponding reduced symplectic form. It is not the standard symplectic form that the standard area form that the sphere has in R3. You have to basically we scale a little bit the standard area form of R3. That's the correct rescaling. And now, if you look in these coordinates at the variation map, you're going to see that that variation map that assigns to each side the volume of the corresponding sphere is going to be the identity map. And just let me write the identity map as 1 times xi. Okay, so this is an instance of a much more general theorem of Deutsch-Markov-Heckman that says the following thing, that if you have a Hamiltonian action of a compact torus and the action is free and proper, then this variation map that goes from the dual of the Lie algebra of the torus with its lattice to the cohomology class of the reduced space and the map which is sending to each reduced space its cohomology class, well, that's an integral affine map. That is, that's degree 1 polynomial, which in those coordinates has integral slopes. All right. So what I'd like to do now is simply restate this theorem in the language of Poisson geometry and foliation theory. So the translation would be the following one. So the right Poisson theoretic object you have to look at is this question of M by the torus, because it happens to be a Poisson manifold. So basically you take the Poisson bracket that you had in the original symplectic manifold, you apply it to invariant functions, which is the ring of the quotient space, and you get another invariant function. And well, that bracket turns the ring of functions of the quotient into a Lie algebra over the reals. And also, crucially, it also has the property that when you fix one entry, you get a derivation, you get the so-called Hamiltonian vector field. Now, some basic theory of Poisson manifolds tells you that this Hamiltonian distribution is integrable. So it gives rise to a foliation, and it's symplectic in the sense that each leaf of the foliation supports a symplectic structure. Now, in this very specific example, the foliation that you get is simply the fibers of this map induced by the momentum map. And the symplectic form that you get is, of course, the reduced symplectic form. Now, what's interesting here now is that you can interpret the target of the momentum map as the quotient space of your foliation. So the foliation is very trivial because it's given by the fibers of a vibration, but still, you can think as the quotient as its leaf space. And the leaf space, which is T star or an open subset of T star, happens to be an integral affine manifold. So if you want, the symplectic foliation that M modulo T has a transverse integral affine structure. So in this language, the Dosser-McHeckman variation theorem says that you have some very specific Poisson manifold. Its symplectic foliation has the leaf space, which happens to be an integral affine manifold, and the map dot sends each point in the leaf space, that is each leaf, to the cohomology class of the symplectic form in the leaf is integral affine. And of course, the natural thing to, or the natural question to answer is, well, are there more Poisson manifolds that have this Dosser-McHeckman property, or just those coming from these free and proper Hamiltonian actions? And well, the purpose of the talk is sketch or present the class of Poisson manifolds that we call Poisson manifolds of S proper type that do have the Dosser-McHeckman property. That is, the leaf space of their symplectic foliation is an integral affine, not manifold, actually orbifold, and the variation map from the leaf space to the second cohomology group of the leaves is integral affine. All right, so let me spell out a little bit the plan of the talk. So I'm gonna discuss first of all, well, let me just tell you from the very beginning that the kind of leaf spaces that we're going to be handling are not much more complicated than manifolds. They will be orbifolds. So the first thing that I want to do is recall or review how does one detect that a given foliation has leaf space, which is an orbifold. And I'll simply stress the viewpoint of holonomy groupoids, how by means of the holonomy groupoid, you can detect whether the leaf space is an orbifold or not. The second part will also incorporate transverse integral affine structures. It's going to be also pretty much expository. And perhaps the key point is that transverse integral affine structures can be controlled by both Lie groupoids and symplectic geometry. And that will take us to the third part of the talk, which is the central one, which is this Poisson manifold of S proper type and the Dostermark-Heckman variation formula. And the connection with the previous parts is that there's a modern view point in Poisson geometry that uses both Lie groupoids and symplectic geometry. And well, that viewpoint that shows up in the previous two parts will make the connection. And the final part of the talk, if time permits, will be about these Poisson manifolds of S proper type whose symplectic foliation is not regular. So we'll see that even though the foliation might be singular, these Poisson manifolds still have the Dostermark-Heckman property. Okay, so pretty much the summary of this first expository part is that among the different ways that one can use in foliation theory to control, to study the quality of a Lie space, the holonomy groupoid, at least for the purpose of this talk, will be the one of my choice. And this is very, very standard material that goes back to Reeve and Hafliger. And if you want a reference in the modern viewpoint using Lie groupoids, the monograph of Mudak and Merchun is a very good one. All right, so my assumption here, for the sake of the exposition, is that I'm going to have a compact foliation. That is, foliation, all whose leaves are compact. And there's a lot of literature in this subject. There are mostly papers by Epstein and Edward Millet and Sullivan, and there are different ways of characterizing when a compact foliation has orbital Lie space. And the one that I'm going to choose is basically the holonomy groups. So we know that the Lie space of this compact foliation is an orbifold, if and only if each leaf has finite holonomy group. So let me spell out a little bit this result. I think that Javier Ribon in his talk already did something like that. So what one would do, so we would be starting in a given leaf, we would take a transversal, and then we would look at the holonomy parallel transport of loops, and then take the germ. Now that would give us the corresponding holonomy group. Now, being that holonomy group finite, results that go back to Reeve tell us that we have a normal form for the neighborhood of the foliation in the given leaf. So the normal form uses the small transversal. It uses the holonomy cover of the leaf. The leaf was compact. The holonomy group is finite, so that is a compact manifold. And then one uses the diagonal action of the holonomy group on the transversal and on the holonomy cover. And that quotient space is precisely the or a tubular neighborhood of the given leaf. And of course, from there, one produces right away an orbifold chart. So one takes the transversal, and then one linearizes the action of the holonomy group. And well, from there, one does that for different sections and builds an orbifold atlas. One has to check, of course, that different charts of the orbifold atlas are compatible using, again, this holonomy parallel transport. All right, what one can do at this point is look at this information in a slightly and even less refined way. That is, what one can do is take the union of all these charts, of all these orbifold charts, and build a total transversal. And for that total transversal, pick all the leafwise paths that start and ends in points of the transversal, and then take its corresponding germ of holonomy parallel transport. What one produces is a Lie groupoid. It's the holonomy Lie groupoid over the transversal. It's a tau, meaning that the source and target map, they are local diffeomorphisms, and well, it's also effective. Now, how does one encode the information that the Lie space is an orbifold using this holonomy groupoid over the transversal T? Well, it's easy to check that one way of stating the condition above is saying that this holonomy groupoid over the transversal is proper. That means that it has to be Hausdorff, and that the map that sends each arrow to its source and its target has to be a proper map. Okay. Now, this construction uses, if you want, an orbifold atlas or a total transversal T, and one can do the same thing with a different total transversal. One will get another holonomy groupoid over that transversal, and these two holonomy groupoids pretty much carry the same information. More precisely, they are equivalents in the sense of Lie groupoids. They are Morita equivalent. And it's important, this is important because, I mean, this notion of Morita equivalence for arbitrary Lie groupoids is telling us something about two groupoids which are Morita equivalent. So first of all, it says that these groupoids have Lie spaces which are homeomorphic. It also says that for leaves which are under this bijective correspondence, the corresponding isotropy groups, in this case, holonomy groups, are isomorphic. And also, and this is crucial, properties such as the properness of a Lie groupoid, they are invariant under Morita equivalence. And that means that rather than using these holonomy groupoids over the transversals, what one can do is basically collect all germs of holonomy parallel transport and then work with the full holonomy groupoid of the foliation. Now, there are several advantages to doing that. One which might be, if you want, aesthetic, is that this is choice-free. We don't have to pick a specific transversal. Another one which is also interesting is that the orbit of this larger groupoid is, or the orbits coincide with the leaves of the given foliation. And whenever we have some kind of problem, we don't like to throw away information. And that's something we do a little bit when we go from the full holonomy groupoid to 1 over transversal. And there's a third very interesting property, which is that this holonomy groupoid actually can be controlled using infinitesimal tools. So there's a Lie functor that goes from Lie groupoids to Lie algebroids, which in this specific case of the holonomy groupoid, what does is giving us the underlying distribution of the foliation. And it also remembers that when we take two sections, there is a bracket, and also that these sections are vector fields of the manifold. So it's more generally a Lie algebroid. So one would say that this holonomy groupoid integrates that Lie algebroid given by the distribution of the foliation. Also, this more general viewpoint is, or this viewpoint is interesting because one can also say that the distribution as a Lie algebroid is integrated by the holonomy groupoid, and that construction is actually a little bit more general, more abstract, and one can actually go to other integrations of this Lie algebroid, such as the monodromy groupoid, meaning that leafwise homotopy classes of paths in the foliation. Okay, so what would be the corollary of this discussion? Well, that if we have an arbitrary foliation and we want to check whether the leaf space is an orbifold or not, one possibility is looking at the holonomy groupoid of the foliation and making sure that it's proper. Note that in the previous exposition, I was making the assumption that the leaves of the foliation were compact, but that's actually something that one doesn't need to require. The reason is that if the holonomy groupoid is proper, then one can pass to a total transversal and we'll get a proper étale groupoid. And the passage from proper étale groupoids to orbifold atlas is straightforward. Okay, so what one can do now is basically look at interesting topological properties of the groupoids. I told you, or I mentioned properness. One can look at source properness, meaning that the source map is going to be proper, or one can require the whole Lie groupoid to be compact. And then one can make the following definition. One can say that a given foliation is of some C type if its holonomy groupoid has that property. And that's simply a way of recasting very well-known properties of foliation by means of the holonomy groupoid. So as we saw, proper type is equivalent to the leaf space being an orbifold. Source proper type is adding the property that the leaves must be compact. And compact type is adding the property that the ambient manifold has to be compact. You can actually be even more demanding and go to strong types, meaning that you put requirements in the larger monodromy groupoid. And geometrically, that will amount to putting constraints on the homotopy groups of the leaves of the foliation. All right, so this section, as I told you, was meant to be expository and simply to highlight the viewpoint of holonomy groupoids, or if you want, of Lie groupoids when looking at some properties of foliation. Now, I want to continue now introducing some very specific transverse structures. So you want the summary of this second part would be that again, Lie group pods can be very helpful if you want to study transverse affine proper foliations, and to show that their Lie spaces, which we know they are orbifolds, are actually orbifolds of a very nice type. They are good orbifolds. They are quotients of manifolds by proper actions of discrete groups. And the second part of this section 2 is showing that transverse integral affine structures, they are actually encoded by both by a mixture of information that comes from Lie group pod theory and from symplectic geometry. And you have there some references, because again, this material, with few exceptions, is very, very classical. So, okay, so let me just recall what an integral affine structure on a manifold is. So it's an atlas in which the change of coordinates belongs to the affine group or to the integral affine group. And one can use a Hafliger viewpoint, because essentially what we're doing is selecting a pseudo group of the pseudo group of local diffeomorphism of Rn, and promote the definition of integral affine structure on a manifold to an integral affine structure on an étal group pod. So that means that we can say, or we can give one possible definition of a transverse integral affine structure on a manifold. There's another viewpoint in which the transverse integral affine structure doesn't use this holonomy group of transversals. It actually uses objects on the whole foliated space. So we would basically use an adapted atlas in which the change of coordinates in the base of the submersion would have to belong to this integral affine group. All right, so integral affine structures, or integral affine manifolds, or transverse integral affine structures, they come with a developing map. And that's simply because affine transformations, they are analytic. And we know that we build these developing maps by means of analytic continuation. So if M was a manifold, we would pick a point, construct a fundamental group based at that point, and basically build the map from the universal covering space to the tangent space of the manifold in that point. If you are in the setting of foliations, the map would land in the normal space to the Lie through that point. We also have an transverse holonomy representation. So that's a map group homomorphism from the fundamental group to the group of affine transformations. One can also pick simply the linear part and have the corresponding linear transverse holonomy representation. And we also have the images of these groups, this sigma F, and also the corresponding sigma lin that one can interpret as subgroups of the affine group or as quotients of the fundamental group. And then that second viewpoint gives rise to the corresponding covering spaces. We have the linear holonomy covering space and the affine holonomy covering space. Now, the first fundamental result that is well known about transverse affine foliation is that this linear holonomy cover with the induced foliation produces a foliation that has no holonomy. And geometrically, this is telling us the following thing, that if we have a path in a leaf, we have a loop in a leaf that produces some holonomy, that loop is detected by the fundamental group. And you can compare this situation with the general situation. For instance, if you are working in the refoliation in S3, so there's a loop in the fundamental group of the torus that has non-trivial holonomy, yet is contractible in the sphere, of course. Now, this foliation without holonomy, in general, doesn't need to have a nice leaf space. And you can think, for instance, of the Kronecker foliation in the torus. And the holonomy, the foliation in the holonomy cover is preserved by this linear holonomy group. And the leaves of the foliation are actually holonomy covers of the original leaves of her foliation. Now, what one can say about this transverse integral affine foliation is that if we assume that they are have orbifold leaf space, that is, if the holonomy group pod is proper, automatically this leaf space, this orbifold, is a good orbifold. And that's something which is pretty much straightforward if you assume that the leaves are compact. The reason being that when you go to the linear holonomy cover, again, because holonomy groups are finite, you're going to have still a foliation with compact leaves and with no holonomy. And that means that its leaf space is orbifold, and no holonomy means that it's a manifold. Now, if the leaves are not compact, the situation is a little bit more complicated, but perhaps the catch-up is that if you use very, very standard methods from Lie groupoid theory, you can equally deduce that the leaf space of the foliation is a good orbifold. What you'll be doing is basically setting up a Morita equivalence between the holonomy groupoid of your proper foliation with transverse affine structure and the action of the linear holonomy group on the base of the linear holonomy cover. And here you have to prove a couple of things. First of all, you have to prove that this B-lin, the leaf space of the linear holonomy cover, is actually a manifold. And there the Lie groupoid methods are useful because, I mean, they allow you to detect it right away. Who is the holonomy groupoid of this linear holonomy cover? And then the properness assumption tells you that this holonomy groupoid is also proper, hence B-lin is a manifold. And then finally, once you have the Morita equivalence, you know that properness is transferred by Morita equivalences, and that's telling you that the action of this group on this manifold is proper, hence you get a good orbifold. All right, so how about what happens when the integral affine structure is enriched? Sorry, when the transverse affine structure is enriched and it's also the integral affine. Well, what happens, perhaps the important observation is that unlike transverse affine structures or affine structures, the integral ones, they can be described by means of infinitesimal data and an integrability condition. So in the case of a manifold, not still in the case of a foliation, you can argue as follows. So you can take an integral affine chart and you can look at the corresponding, the one forms corresponding to the integral affine coordinates. These are exact one forms and they span a lattice. And if you want to get rid of coordinates and give a coordinate-free statement, what you can say is that this lattice is formed by closed one forms. So that's the exact equivalence of an integral affine structure. And now, at this point, symplectic geometry kicks in because we know that closed one forms in a cotangent bundle with the standard symplectic structure are Lagrangian manifolds. So you can say that the integral affine structure is given by Lagrangian lattice. You can move on and take the quotient of the cotangent bundle by the lattice with the induced symplectic form. And now you're in a symplectic manifold whose fibers are Lagrangian tori. So it's a Lagrangian bundle of tori. And well, it is a situation which is very well studied in symplectic geometry. And actually, this is the best possible Lagrangian fibration that one can encounter, precisely because the fibers are tori, and also because the fibers are not just topologically tori, but they are groups. So that means that there is a global Lagrangian identity section. All right. So what's the result? What's the end product that we get here? This quotient of the cotangent bundle by the lattice. Well, that's an object that is well known in Lie groupoid theory because that's a torus bundle. That's Lie groupoid, and then it comes with a symplectic structure that is compatible with the multiplication of the Lie groupoid. It's what we call a multiplicative symplectic structure. So that parlance of symplectic torus bundle is an object of, if you want, symplectic Lie groupoid theory. So integral affine structures are encoded by data in symplectic Lie groupoid theory. Going from manifolds to foliation, that is from integral affine structures to transverse one, doesn't change the picture at all, essentially. So now the transverse integral affine structure produces a lattice in the conormal bundle. Now the conormal bundle is still inside the cotangent bundle, so you can still say that the lattice is Lagrangian. You can take the quotient, and then you will get a bundle of tori that now won't be Lagrangian with respect to the symplectic form, yet they will be isotropic. And also there's an important property of the induced symplectic form, sorry, the induced two form. So these two forms won't be symplectic, but its kernel won't mess up with the vertical directions. And again, that property is describing an object which belongs to Lie groupoid theory. So that's a so-called presymplectic torus bundle. All right, so the summary, if you want, of this second part of the talk is that these transverse integral affine structures, they are encoded by means of Lie groupoid theory and symplectic geometry. And this takes us directly to the relation with Poisson manifolds. So there's a classical way of introducing a Poisson structure. It's the one that I used at the beginning of the talk. So you have a bracket in the ring of functions that make that ring into a Lie algebra over the reals, and you also require that the bracket be dynamic, that it produces derivations. And right away, I mean, there's this very classical view on Poisson geometry that sees the subject as a mixture of three areas. So on the one hand, you have foliation theory, because the Hamiltonian distribution integrates into a foliation. On the other hand, you also have symplectic geometry, because the leaves of this foliation carry symplectic structures. And finally, you also see classical Lie theory appearing into the picture. So one quick way of seeing that is the following. So here we have S is a symplectic leaf of a Poisson manifold. One can take a transversal, and one may have nearby leaves of different dimension, but doesn't matter. But on this transversal, there's an induced Poisson structure. That Poisson structure vanishes on this point, and that means that one can linearize it, and one can produce the corresponding linear Poisson structure in the normal space to the symplectic leaf. And well, if one dualizes that data, one is going to find is simply a Lie algebra. So if you want, every Poisson manifold comes with a Lie algebra attached at each point. And when you're doing Poisson geometry, what you're really doing is studying the very, very subtle interaction between these three areas. Okay, if you look at these three areas separately, you'll see that each of them has a notion of compact object, which makes it possible to develop a nice global theory. So in the case of foliation theory, the nice compact objects would be compact foliations whose leaf space is an orbifold, the ones we discussed until now. In the world of symplectic geometry, the compact objects are compact symplectic manifolds, whose theory is much, much richer than the one of arbitrary symplectic manifolds. And in the world of Lie theory, the nice compact objects are the compact Lie algebras, so the Lie algebras of compact Lie groups. And well, the natural hope is whether one can give a notion of compact object in Poisson geometry in such a way that some of the nice properties that we see in foliation theory, in symplectic geometry, and in Lie theory can be carried over to these compact objects in Poisson geometry. And one can do that, and the way to proceed is basically to use a viewpoint on Poisson structures, which has been widely used in the last 20 years. And that means regarding a Poisson structure as a Lie algebroid structure on the cotangent bundle of the manifold. So it's not very important to give or to spell out the definition of a Lie algebroid structure. Maybe just telling you what's the philosophy behind the idea. Now, if you stick to the viewpoint of an infinite dimensional Lie algebra, if you try to integrate an infinite dimensional Lie algebra, the only object that you can think of would be some infinite dimensional Lie group. In other words, you cannot integrate the brackets of a Poisson manifold into a finite dimensional object. However, if you're working with a Lie algebroid, those Lie algebroids sometimes, not always, they integrate into finite dimensional objects. So your hope is being able to tame what happens in Poisson geometry by requiring this integrability condition. So as I told you, not every Lie algebroid is integrable. It's not the Lie algebroid of a Lie groupoid, but we know full well which Lie algebroids are integrable. So that's work from by Kreinig and Fernandez around the year 2000. So we can give the following definition. We can say that a Poisson manifold is integrable if its cotangent Lie algebroid happens to be integrated by a Lie groupoid. Now, what are we doing when we single out the class of integral Poisson manifolds? What do we get? What extra property are we getting? Well, so Kreinig and Fernandez described this in a very precise way. So for a Poisson manifold being integrable, that means that the symplectic structures of the leaves vary in a reasonable or in a controlled way when we cross from leaf to leaf. So you see, it has to do, in some sense, with the Deutermann-Heckmann phenomenon. At least there's some relation. Let me also tell you that if a Poisson manifold is integrable, one can choose the largest integration, and that integration carries a multiplicative symplectic form. So a symplectic form that behaves well with respect to the Lie groupoid structure. So you can think of this symplectic Lie groupoid as a desingularization in some sense of your given Poisson manifold. So you have some singular brackets and you replace it by non-singular brackets. All right, so one can now propose the following definition. So we say that the Poisson manifold is of some type C if there exists a symplectic groupoid which has property C, which, remember, that was a topological property, like being proper, being source proper, being compact. And of course, this groupoid has to integrate the cotangent Lie algebroid of our Poisson manifold. All right, so that would be our notion of compact object in Poisson geometry. Now, let me assume from now on that we're working with a compact manifold of one of these types whose symplectic foliation is regular. Now, in this situation, we can apply a very nice result of Moerdijk, which essentially tells us that this symplectic groupoid fits into an exact sequence. Now, what we have on the left is simply a bundle of Lie groups. So these Lie groups is basically collecting for each point in the base its isotropy group and then singling out the identity component. And if you do that, and then you quotient G by T, basically what you are getting is isotropy groups which are discrete. In other words, what you have here is an étale Lie groupoid which integrates the symplectic foliation. So you can think of it as the holonomy groupoid of the foliation of the Poisson structure, but in practice, it will be, or in general, it will be a Lie groupoid that sits in between the holonomy and the monodromy groupoid. All right, that only uses the fact that this Lie groupoid G was regular. Now let's use that this Lie groupoid comes or integrates a Poisson structure. So this is giving us some information about these isotropy groups. Specifically, these isotropy groups, they have to integrate that linear transverse Poisson structure that I mentioned a few minutes ago. Now, because we are assuming that the Poisson manifold is regular, it's well known that this transverse linear Poisson structure is trivial, given by a trivial Lie algebra, an abelian Lie algebra. And that's telling us simply that these groups are abelian. Now, finally, let's apply property C. So if we apply property C, what we're going to see is that both the Lie groupoid T and the Lie groupoid E, they inherit that property. And for the Lie groupoid T, it means that these abelian groups are tori. And if we restrict the symplectic structure that we have in G, we're going to end up with a bundle of tori endowed with a multiplicative symplectic form, actually, that turns it into a presymplectic torus bundle. Now, if we go to the right-hand side of the picture, what happens is that this Lie groupoid E that integrated the foliation has property C, and hence so the foliation. And well, if you put the left-hand side and the right-hand side together, what you end up showing is that the leaf space of this symplectic foliation of the Poisson manifold is an integral fine good object. So at least at the level of leaf spaces, what we see is that this class of Poisson manifolds of some compact type, they come with very, very nice leaf spaces that in particular carry an integrally fine structure. Okay, so from there, at least one can state what would the global Deutsch-Heckmann variation formula would be. So non-precise statement would be the following. So if we have a Poisson manifold of a proper type, and using this condition to make sure that the leaves of the symplectic foliation are compact, so I can have nice control on the second cohomology group and can make sense of a bundle of second cohomology groups. Now, in this case, what's going to happen is that the cohomology classes of these synthetic leaves, they are going to vary in an integral affine fashion. So more precisely, what one has is that commutative diagram. So let me at least rewrite this diagram in the classical case when we have a Hamiltonian S1 action on the manifold M. So in that case, one actually would work locally around one reduced space. So I would take the interval minus epsilon epsilon, and then one would map to the second cohomology group the reduced spaces, and this would be this variation map. So the cohomology class of the corresponding reduced space. That diagonal arrow would be simply the identity map. Here we would have this very same interval. And this affine variation map on the right-hand side, what's really doing is sending T to the cohomology class on the reduced space at 0 plus T times the derivative at 0. And the commutativity of this diagram is telling you that the variation is affine. And then the integral affine part would tell you that this slope is an integer. Now, if you want a global statement, what you have to do is basically work with the fundamental group or with the fundamental groupoid of your Poisson manifold, then take this bundle of second cohomology groups of the leaves and lift the variation map to the universal cover where this bundle is a product. So specifically for a given path, you would be making parallel transfer with respect to the Gauss-Manning connection of the cohomology class at the value 1 to the cohomology class at the starting point of the path. Then you will also have this developing map, which is responsible for encoding the integral affine structure. And then this map, well, would allow you to basically compute the derivative of the variation map. So you would use the Gauss-Manning connection to take the corresponding derivative. And you have commutativity of the diagram. And that would tell you that the cohomology classes vary in an affine fashion. And to add the adjective integral affine fashion, you need to show essentially that the image of this bundle inside of H is an integral affine subbundle. Well, anyway, so that would be the statement of the global version of the integral of the Torres-Heckman theorem. Don't think I'll say anything about the proof. Let me simply recall that I already mentioned that just integrability assumption was taming in some sense how symplectic forms of synthetic leaves vary transversally. And if you put on top of that the compact type condition, that taming becomes integral affine. So let me not say more about that. And simply go back to the classical Torres-Heckman theorem. So why is it a special case of what I showed you before? Well, because if we have this free Hamiltonian action, free and proper Hamiltonian action of a torus, in the Poisson picture, we have to look at this Poisson manifold of the quotient of the manifold M by the torus with the corresponding Poisson bracket. And this is a Poisson manifold of S proper type. That is, one can build explicitly a symplectic groupoid of S proper type that integrates it. It's very, very straightforward. One takes two copies of the symplectic manifold with the symplectic form plus its opposite. There's a diagonal Hamiltonian action of the torus, and one simply takes the reduced space at level 0. And this happens to be a symplectically groupoid of S proper type, integrating the Poisson structure on M modulo T. So if you run our somewhat complicated machine for Poisson manifolds of the compact type, you would get the Torres-Heckman property, variation property. But of course, you can run this machine for examples which are more general than Hamiltonian free torus actions. So I guess I have like a couple of minutes or three, I don't know.
Yes, yes, David, a couple.
Okay. So let me just very briefly tell you that if your Poisson manifold of its proper type happens to be not regular, it has a singular symplectic foliation, still there's a way of proving the Deutsch-Mark-Ekman property. And the main idea behind is that there's a process that resolves your singular foliation into a regular foliation. So let me show at least the picture in a very simple example. So what you have in the right-hand side is the symplectic foliation of the dual of SU2, that is concentric spheres. And here in the middle, you see the singular leaf. Of course, there's a very simple-minded way coming from differential topology to produce a regular foliation, which is blowing up the origin. If you do that, and you look at the corresponding leaf space of this regular foliation, you're going to see that indeed you have an orbifold, because it's the reals with the action of Z2. And in fact, you know this from Lie theory, because Lie theory tells you that these adjoint orbits, their leaf space is basically a Cartan subalgebra or its dual modulo the Weyl group. So in some sense, what you can think about this blow-up construction is a geometrization of an statement which is purely coming from Lie theory. That is, what you're doing is geometrizing, giving a geometric version of the Weyl group. This Weyl group now here appears as the holonomy group of the RP2 leaf that one produced. And the important remark to be made here is that this process doesn't change the leaf space. What you're doing is inflating a leaf that didn't have the right dimension. Okay, very fast. That previous blow-up construction can be done for arbitrarily Lie algebras, but it's not a blow-up. So doing a blow-up is a little bit simple-minded. So there's a process, there's a theorem in classical Lie theorem that it's Weil's covariant theorem, and it's doing the right blow-up for you, the right resolution. And the nice observation is that you can rewrite Weil's covariant theorem using only the language of Lie groupoid theory. And that means that this process is valid for any Lie groupoid. Now, if that Lie groupoid is good enough, it has C-type, what you're doing basically is desingularizing its singular foliation. So again, we have this Poisson manifold, we desingularize it, we produce a foliation which is regular, and we're not changing the leaf space, we're appropriately inflating singular leaves. And you end up with a manifold, which is not longer Poisson, it's what we call a Dirac manifold, but it has still the right C-type. And that's telling you that this leaf space is an integrally affine good orbifold, which means that your original leaf space is an integrally affine orbifold. And with some more work, now you can state the Deutsch-Mark-Ekman variation formula, and then using techniques a little bit more refined than in the regular case, you can actually prove it. All right, so let me finish the talk parabenizando mais uma vez ao Paul. Muito obrigado. Thank you.
Well, thank you, David, for this very conceptual explanations. Are there questions? Are there questions
Can you hear
online?
me?
Yes.
So can you go back to the how do you say example? But I do want more concrete example. No, said it before.
The example at the beginning of the talk?
In a triangle, in a diagram.
I remember. So I think you meant in the theorem, in the Deutsch-Mark-Ekman theorem.
Yeah, that's it. That's it. Yes.
Okay. So the example is this, the Hamiltonian action of S1, and what you would have. So what here would be your manifold. Actually, what you would need to put here is the reduced symplectic space times the interval. You would be parametrizing reduced symplectic spaces. And you, in some sense, you basically forget about the reduced space factor because it's not very relevant for the computation here. So here is just the parametrization of the reduced spaces. So for each one, you write down the variation map, which is the cohomology class of the corresponding reduced space. And that diagonal part, you don't use it here because, I mean, the integral affine structure is already visible by the embedding of the interval in P star. And that part here is really the linear variation. So what you do is you're basically sitting or centering the problem at the value t equals to 0, and you compute the cohomology class of the reduced space at that point, plus t times the derivative, the variation, the infinitesimal variation at that point. And that's a map that goes from here to here. And the commutativity of the diagram is telling you that the variation, essentially that var, call this var affine, if you want, that the variation of cohomology classes is affine. And then you have to take that slope, which if you want is a Chern class, and just remember that, well, this Chern class is integral, of course, it's an integral. And in the more general case, you already have an issue because your leaf space is not just an interval, it can be a complicated integral affine, not even a manifold, an orbifold. So you don't want to work with the leaf space. You want to work with the original given Poisson manifold with M. So that's a little bit large. So you would then take the fundamental group or the fundamental groupoid, and then you would use here the developing map basically to get hold of the integral affine structure in the leaf space. But this part here would be exactly the same one. It would be the affine variation. You would take the section of cohomology classes and you would take the derivatives using the Gauss-Manning connection. So that would be like your affine version of this map, and the commutativity would tell you that the variation map is really fine.
Okay, thank you.
Other questions? Well, let us thank David again.
Thanks a lot for listening. And mais uma vez, parabéns, Paul.
So we resume at 10 to 3. Now we have a coffee break.